Yeah, I agree. I think we need to take the test and push it to next Thursday.
I already took my day off.
What?
I took the day,
Tuesday?
yeah, I took the morning
To
off.
study?
Yeah.
Great. Then you'll have 48-hour, even more time.
Now, when you say next Thursday, is that like Thursday?
That would be the class before the final. Yeah, so you wouldn't really want that.
We have a whole week off for school?
Hmm?
I'm not,
we have next week.
yeah,
We have the week after that.
okay,
The following week are finals.
okay, so we have 2 more weeks.
We have 2 more. The week before finals, we still have to cover a couple of things, but you'll love it. It's gonna be easy. That'll be before the final. You're gonna bring it to the final. Is the final on Thursday? Then you don't have we don't have class on that Tuesday. That's right. I'll be giving a final that Tuesday. That'll be starting at 11 and ending at 3. I'll be around. Yeah, I'll let y'all know. That's what we'll have to talk about. Yeah, what I'd like to do is make it where if you want to do a retake, then you would have to come in on like one of my other days I'm giving a final to one of my other classes and take the final during their final time. But we can work it out. I mean the day of our final? Yeah, because that's the Thursday. Okay, yes. If you have the bonus, please put it on the corner of that desk right there, because that's what we're starting class with. I uploaded it last night, late. I thought I had uploaded them, and someone texted me that it wasn't there, so I put it out there. It should be. Okay, can we get started? We have a lot to do today. So this function, anyone else bonus now? Okay, this function, s of x equals x plus 100 over x with x being greater than 0, was a function that we came up with that would give us what the sum of two positive numbers were, right? But those two numbers had to multiply to be 100. Yes? And so what we have is a function, and we're trying to find the maximum, right, or the minimum. What was it? I don't remember. Was it minimum? Let me go back to find two numbers, both positive, whose product is 100 and sum is a minimum. So we figured out a relationship between x and y. We came in here, we came up with this function. I said we would start class with this. So let's try and find the the minimum value of this function. So the first thing I'm going to ask you is, what is the domain of this function? X can't be 0, but remember we said these were positive numbers? Yes? So x can't be negative either. So the domain is everything from 0 to infinity, not including 0. Now, is this a closed interval or an open interval? It's an open interval because to be closed, you would have to have brackets on both sides, including two numbers. Now, we have two ways of finding the maximums and minimums of a function. We have the closed interval method, and then we have what we learned with the graphing of functions where you can find where your local max and local mins are, and those did not require a closed interval to do it. So is everyone clear that there are two different approaches to finding highest and lowest points on a graph? Because this is open interval, we cannot use the closed interval method. So we have to find the derivative of this, right? Find the critical numbers, draw them on a number line, pick test points, figure out where this thing's going up and down and up, and then from there identify our minimums, or our minimum. All right, so first thing I'm going to do is take the derivative of this function. The derivative of a sum, I just do the derivative of the first one, which is 1, right? And then the derivative of the next one is negative 100 over x squared. And I did that by rewriting this as 100 x to the negative 1. Right, that's what that is. Bring the x up, has a negative exponent, and then use the power rule. Derivative of this, negative 1 comes out. Subtract 1, x to the negative 2. So that becomes this. Are we clear on that? Yep. Now, this is our derivative. We find the critical numbers. We figure out where this is 0. We figure out where it is undefined, right? Where it doesn't exist. So where's the derivative equal to 0? So we take our derivative, we set it equal to 0. And for this, I'll get a common denominator because that seems to be the approach that I've used a lot, right? Common denominator between these two becomes x squared over x squared. I'm rewriting the 1 as x squared over x squared. Then the 100 over x squared I'm not touching. Now I can combine these two together. X squared minus 100 over x squared. And when is a fraction ever 0? Only when the top is 0, so I set the top equal to 0. And that gives me x squared is 100. I take the square root on both sides, and I get two possible solutions, plus or minus 10. But x can only be positive, right? So I throw out the negative. X must be greater than 0, so x must be 10. All right, that's one of our critical numbers. Do you all agree? All right, the other thing I need to look at is where the derivative doesn't exist. And where would this derivative have problems? At 0, yes? But is 0 in the domain of our original function? No, it's not. So you cannot have a critical number that doesn't live in the domain of the function. It's not possible, right? Or we don't consider it. So even though x can't be 0, right? We don't consider this since the domain is 0, not including 0 to infinity. All right, so once I have my critical numbers, in this case number, I draw it on a number line, right? So I have to go to a new page. Here's 10. I need to pick two test points, one here and one here. Now, when you pick these test points, they can be anything to the left of 10, but it has to be in the domain of the original function. So you can't pick negative 10 or negative 5. It's got to be between 0 and infinity. So I pick something like 1. And then over here, I pick anything bigger, so maybe like 20, okay? And where am I going to plug these values in? To the derivative. So I do the s prime, sorry, it's not f, it's s prime of 1. Let's see what we get. The derivative was 1 minus, right? 100 over x squared, which would be 1 squared. That's 1 minus 100, isn't it? All I'm concerned with is what, though? That this is negative, right? So that's below 0, that's less than 0, negative 99. So what does the first derivative being negative over here mean? It's decreasing. What's decreasing? The original function, right? S is decreasing. My sum function is decreasing. The derivative is negative. The original function is decreasing. Then we plug in 20 into the derivative again. This time you get 1 minus 100 over What's 20 squared? 400. And that's 1 minus a fourth. And that number is positive. And that's what I was really hoping to have, right? Because that tells me my original function is going up there. If my original function goes down, and then at 10 it switches and starts going up, and 10 is in the domain of the function, right? It is actually part of the function. The function can be evaluated there. Then this should represent a local minimum, right? In fact, it should be the only minimum, because if the function goes down and then goes up and never does that again, that should be the lowest point on the graph. Therefore, that's going to be what we use for x to make this thing be the minimum. So we have a minimum. Let me write this. S has a minimum when x equals 10. Now let's answer the question, the original question. Find two numbers that are both positive, right? Whose product is 100 and whose sum is a minimum. Two numbers. Right now I have just x. You have to go back and look at last class. The other number, we called it y, didn't we? And somewhere in here, we had an equation for y, didn't we? You have to go back into your work and find your equation for y to figure out what y is. In this case, y will be equal to 100 over x, but we just said x had to be what? 10? So it's going to be 100 over 10, which is going to be 10, which kind of makes sense. I mean, two numbers that multiply to be 100, 10, and 10, that's the smallest it could ever be when you add them together. Didn't we do a table? Oh, here were some examples over here. We did like 2 and 50, right? We thought 10, so we were right. Our guess was correct. But as you'll see today, the guessing part of it goes away pretty quickly when the problems become more complicated. But this was just to get us thinking optimization. All right? Let me finish this up by writing out. Okay, therefore, 3 dots, right? Therefore, y is 100 over x, which means that y is equal to 100 over 10, which means that y is 10. So the two numbers are 10 and 10. Questions? No? All right, so that was just last class, was just to get us going like thinking optimization, but let's actually look at what the section notes say about optimization. Okay, we've reached a point where we can apply what we have learned so far to some interesting word problems. I'm using the word interesting. Interesting word problems. You could replace that with difficult. You could replace that with stressful. Here are the basic steps. All right, here are the basic steps. Read and understand the problem. Understand what's being asked. Read it twice. Read it 5 times. However many times it takes to understand what is being asked. Draw pictures. If possible, draw pictures. In the problem I did with the two numbers, we didn't really have a picture, right? Didn't really have anything. Introduce notation. Introduce notation. Variables. Introduce things. Call things x, y, z, whatever you want, right? You introduce that into the problem. Determine the variable to be optimized. In the problem with the two numbers, what was it that we wanted to optimize? We wanted to find the minimum of the sum, right? The sum was the variable we wanted to optimize. The S, right? The sum. That's part of what these problems entail. You have to identify the variable that you want to optimize. We call that the objective function or the objective equation. right? Our objective equation was, looking back in your notes, our original objective equation was this. S is x plus y, right? That's what it was. We wanted to find the minimum value of s if you have two numbers that you're going to add together, right? Then express the variable to be optimized in terms of other variables. Well, actually, that's this right here. Express the variable I want to optimize in terms of the other variables, x and y. Then use the given restrictions or the given information to express the variable to be optimized in terms of one single other variable. So when we were here, we could not find the maximum value of s, or the minimum value of s, because it had two variables, right? X and y. But we used the given restrictions. The given restrictions that for that problem were that x times y had to be what? 100. That was a restriction. I called this a constraint. Do y'all remember me calling it this? I know it was at the end of class. But we called that the constraint. And so what we did here is we solved this for y and got y was 100 over x, right? That's my constraint on y. Y must have this relationship with x. So using that restriction, I expressed the variable I wanted, s, in terms of a single variable by replacing y with that. Now my expression for s has one variable instead of two. Yes? Understand? Questions? After we've done that, we basically have a function. S is now a function of x. Right? It's a function of x. And once you have it as a function of a single variable, you use the methods of this section to find the absolute max or minimum values of the function. And that you'll either do closed interval method or open interval method, depending on the problem. Pay special attention to whether or not your function is defined on an open or closed interval. Use that to determine your approach. All right? That's the basic idea. Sounds okay? Sounds difficult? All right, find the maximum area of a rectangular pen. So like imagine like you're going to build a pen for like chickens or something like that, right? And you want to make a rectangle. You want this, what you have is 100 feet of fence. But you would like to have the most chickens you possibly can in this 100 feet of fence, right? So there are many different ways you can build this fence. And what I have here is an illustration of different variations of what I could do. Could I build a pen that would be 5 feet wide, 45 feet long? Yes? Because I would go 5 feet, 45, that would be 50 feet of fence, then another 5, and then another 45. That would use all 100 feet of fence, wouldn't it? But if I multiply 5 times 45, the area is 225. So that's one way I could do it, right? And the area of that's 225. But then I could decide, you know what? I don't want 5 on that side. I want 8 on that side. So I could do 8 here, 42 here, 8 here, 42 here. That's still 100 feet of fence. But now look at my area. 8 times 42 is 336. This was better, right? The question is, how do I build it to get the most area? So I'll keep moving this, and let's just kind of keep an eye on the area. Area, as I got bigger here, I started out real narrow, got bigger. The area is getting bigger, right? Bigger, 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 bigger. So what is it? Just the bigger I go, the bigger it gets, or what? What's going to happen eventually here? Let me go back to smaller picture here. What's going to happen eventually? 625, now look, 624, 6. Now it's going down, isn't it? It looks like it happened right in the middle somewhere, right when you have, what, 25 by 25? Does it make sense that that should be the right answer? Now, Again, remember, we're starting with basic problems because the more complicated ones, you cannot just say, yeah, 25, 25, you're done. But we should, at least when we get to the end of the answer on this one, we should all have, I guess, been thinking the same thing, like 25 makes sense that it would be the right answer. Go with me? Okay. So let's go through these steps. Read and understand the problem. Draw pictures. So time for me to draw a picture. I'm going to build a rectangular pen. 25 by 25 meant that we should use a square, right? Okay, but we're going to act like we don't know that. There's my picture. What is it that I'm trying to find the maximum or minimum of? Area. By the way, if you're trying to find the maximum or minimum of something, that's called optimization. I kind of felt like that was obvious, but let's just be clear. If you're trying to optimize something, you're trying to find the highest or lowest value of something. So I'm trying to find the maximum area, right? Finding max area. So I'm going to call that variable A. Yes? Here's my rectangle. Introduce notation. Determine variables to be optimized. Have I done that? The variable to be optimized? A, right? A is what I want to optimize. Express the variable to be optimized in terms of other variables. Okay, so do I have any other variables yet? No. So length and width, right? Like this side and this side, I should call them something. We can't say 25. We don't know that yet, right? So I'm just going to call it, I'm going to go X and Y just because we're so used to using X and Y. So now can you express your objective? Can you describe your objective variable, the thing you want to optimize? Can you just describe it in terms of the other variables? A equals XY, right? Area is length times width. Okay, great. We have got the objective equation, don't we? But that's not good enough because for us to do max and min, don't we need to be able to have a function of a single variable, right? How many of you have to take Cal 3 at some point maybe in your life? In Cal 3, we actually have a way of finding the max and min of this without having to go to a single variable. We can do it with two variables. We can have an equation of two variables and we can still find its max and mins. You can even have 3 variables or 4 or 5 and it doesn't matter. So it's later on we would attack this a different way. But for now, Cal 1, this is the way we do it. So what now? Stepwise. Express the variable to be optimized in terms of the other variable. Check, we've got that done. Yes. Use the given restrictions, the information that we're given, to express the variable to be optimized in terms of a single other variable. So right now, I need to somehow get this A to be a function of just 1. But I need to use some information that's been given that I have not used. What have I not used? My constraint. What's my constraint in this problem? What's the constraint? Should I bring the problem back up so you can read it? Find the maximum area of a rectangular pen if you have 100 feet of fence. That means I can't just build some arbitrary pen, right? I'm going to run out of fence. And I want to use all 100 feet, right? It wouldn't make sense to say what's the maximum area and then you use only half the fence. I mean, you've got 100 foot of fence to work with. So what is my constraint? 2x plus 2y has to be 100. In other words, you're saying that the sum of all the sides of my rectangular pen have to equal the amount of fence I have, right? So with this constraint equation and this objective equation, I'm trying to get the objective in terms of one variable. It could be either one. You could go and replace this x with something or replace this y with something. And really, that's up to you. You have complete control of that. A lot of times, though, that will be dictated by how easy it is to solve for that variable here. So do you agree that it would be equally easy to solve for x or y here? It'd be the exact same process, basically. Okay, then I think what I'll do is I'll solve for x just to show you kind of a different look of, you know, our end function is going to be a function of y instead of x. So watch what happens here. I'm going to solve the constraint equation for x. So I move to y to the other side. Then what? Divide by 2. So x is 50 minus y. Agreed? Okay. Now, come to the objective equation, come back to this, and rewrite the area, but I'm going to replace x with what? 50 minus y, so I have 50 minus y, and then times y, which is really just $50y minus y squared, isn't it? Notice what I did on the left side. Instead of writing a, I wrote a of y. I used functional notation. Why am I using functional notation? Because I want to stress that it's a function now. And if it's a function, we can graph it. And if we can graph it, we can find max and mins. That's always the point of this, is to get an objective function that you can determine max and mins of. So now what I'm going to do is determine its domain, because I need to know if I'm going to be doing the open interval method or closed interval method. So the variable we have here is y. Can you tell me some restrictions on y? Like, what would be the smallest value that y could be? 0, right? So you got 100 feet of fence, and you lay out, you basically say, okay, I'm going to build it. Here's x. Here's y, right? You're going to say y is 0. If y is 0, here's your x, right? How long would your x be? 50. You have to be a little careful here, because x has to be both sides of the rectangle, right? But then your y here is 0, which makes no sense at all. Your chickens can't survive in a pen that has no width to it, right? But it's still possible to let y be 0, isn't it? It doesn't make any sense, but like in terms of building something, it doesn't make sense, but it's not algebraically wrong. Are you with me? Okay, so y being 0 would be the smallest. And what's the biggest it could be? 50. We have to use that same logic. It could be 50 because, remember, if you're building a rectangle, y has to represent this side and this side. If you say y is 100, then that means you would let two sides be 100. That means you have to have 200 feet of fence. So you cannot do that. All right? Another way you could do that is just go into this equation right here. If you let x be 0, sorry, if you let y be 0, what's x? 50. If you let x be 0, what's y? 50, same thing. So either way, we get a maximum of 50. And it could be 50, right? Could be 50. Exactly 50. Wouldn't make sense, but we could. And now what we have is a function, right? Continuous function. It's a polynomial. It's continuous on a closed interval. And so I'm going to use the closed interval method. Any questions? Well, kind of. I mean, I don't want to say every problem you're going to plug 0 in for each one. For this problem, yes, because our variable represented the length of a side of a rectangle, and we could let that be 0. So it seemed natural for us to start with 0, right? Wouldn't make sense for us to say, oh, well, you could let y be -2. You can't have -2 feet of fence. Okay, so how does the closed interval method work? Tell me about it and then I'll do it. What is closed interval method? What do? Find the critical numbers. So that's the same, right? What do you do after you find the critical numbers? Plug those numbers and the endpoints into the original function. There's no number line, there's no test points, there's no up, down. It's simply find the critical numbers, take those and your endpoints, plug them into the original function, and we're done. We compare those. All right? That's because it's closed interval. Yep. So I still need the derivative. I'll call it a prime of y. What's the derivative? 50 minus 2y. I figure out when that derivative is 0. 50 minus 2y equals 0. Y is what? 25. Doesn't make sense that we kind of felt like we were going to get 25, right? Okay. What about the derivative being undefined or not existing? Yeah, it's a linear function. I mean, it's very well behaved. There's no issues with division by 0 or anything like that, so we don't have any problems here. Okay, so now I take this and I'm going to evaluate the original function a at each endpoint and at any critical numbers I had. Right? Remember, I'm going into a, not the derivative, right? A. So go to your a function right here. Plug in 0. What do you get? 0. We kind of knew that, right? Like if we let y be 0, you don't have a rectangle. It's going to have no area. What about 50? Plug 50 in here. 50 times 50 is 50 squared minus 50 squared. 50 squared minus 50 squared is 0. So you get 0 again. And then plug in 25. So 50 times 25 minus 25 squared should be 625. Right? Which of these are we looking for here? The max, right? So we are looking at this one, right? That's the max. 625 is bigger than 0. What's that? Can I do what? The graph? This, oh, okay. I didn't know what you... All right, so answer the question. We have not answered the question. What does the question say? Find the maximum area. So what is the answer to our question? 625 square feet. Square feet. So we have to answer the question. So the maximum area is 625 square feet. And just because I want you to see this, if the question had said, find the dimensions of the pen that gives you the maximum area, then they wouldn't be asking you for the maximum area, would they? They'd be asking you for the dimensions. So what would the dimensions be? 25 by 25. You do all the same work, but at the end, what's interesting to you or what you want to know is what this was, right? Y was 25. How do you figure out what x is if y is 25? Come back up here, find your equation for x, and plug in 25 for y, and you figure out what x is. So I'm just going to put below this, the dimensions would be y is 25 feet, and x would be also 25 feet. So 25 feet by 25 foot, a square. That's right. Remember when we were doing local, well, I'm not sure where you're going with that. That's right. And do you remember when we were doing that? I said that the local maximum is actually the y value, which would be like the 625. But I always wanted you to write your local maximums and mins as points. The reason I wanted you to do that is because I want you to understand that in these word problems, depending on the problem, it could be asking for the y or it could be asking for the x. It depends on the problem. So I wanted you to see that they're both important pieces of information. One of them is where it happens. The other one is what value comes out of it. Okay, so far we okay? Two relatively easy problems, relatively easy. It's hard to say relatively easy when you haven't seen the rest of them yet. Okay, so here's the next one. A can must hold 1 liter. So I'm going to construct a can. I don't have a can. I see a can there. I only see one can on desk. So would you mind modeling your can for us? Thank you very much. This is a Monster energy drink. It is a aluminum probably can. Let's suppose with black, I mean, it's awesome, okay? We want to manufacture 1 liter cans, all right? We want to find the dimensions of the can. Find the dimensions of the can with the smallest surface area. Why in the world would we want that? You use less aluminum, right? If we're going to have to make these cans and we're going to manufacture them, we have to buy aluminum from someone, right, to make it? And we don't want to waste money by buying more aluminum than we want. So here's some examples of cans that I could make. I could make a can that would hold 1 liter that would look like that, right? Good. I mean, imagine a can, right, like this. Yeah, right? Imagine my can was like this, right? And I'm walking in, I put this on my desk. I want to take a drink, and I'm like this, right? You've seen those like yards of beer, like during St. Patrick's Day, or is that why they do it? St. Patrick's Day, or is it just all the time? Disney, yeah. I've seen like margaritas and pina coladas, and no matter what, right, they'll just put in there. So you could have that, sure, right? Or you could do a can that looks more like this. Whoa, wrong way. Like this, right? Imagine walking in there and, you're like taking a sip of this thing, right? Might fit in your backpack easy. I don't know, just slide it in there. Right? I mean, you could do this. So it seems ridiculous to do that, right? And so you would think that, well, the can should fit into the human hand and all that, right? I mean, there's certain things that make sense, but it actually turns out that the dimensions of a can are based upon using the least amount of aluminum, all right? And so what I've done is I have the computer here telling us what the volume is. So notice that the volume here is not going to change. As I move these things around, notice the volume is always 1,000. See that? But I want you to keep an eye on the surface area. If I make a can that looks like this, look at my surface area on this ridiculous pole can, right? 857 square centimeters is the amount of aluminum I would need to make that can. Now, if I try and make it a little shorter and a little wider, look what happens to the surface area. It's coming down, isn't it? 600, 655, 5, 550, 554. Uh-oh, what happened? Somewhere in there, right? Somewhere in there, I hit like the minimum amount of surface area. And then once I went past that, it starts going back up 600, 700, 800, 1,000, 1,300, 50. So there is some optimum solution to this, right? And we, as business owners, are interested in not wasting our profits, right? We want to make money. Okay. Everyone understand the framework of the problem? All right, so now we go through and we try and figure it out. So what is the first thing I'm going to do? Draw some pictures, right? Figure out what it is I want to optimize. So here's my can. Do you see how this problem is not as easy as, oh, 10 times 10 is 100, 10 plus 10 is 20? Or a rectangular pen, 100 square feet, oh, 25, 25, it's a square. See how this one is not that simple, right? So here's my can. What is my objective? What is it that I'm trying to optimize? Surface area. Let's just use, I could write SA for surface area or just A, as long as everyone understands that what I mean by A is the surface area of the can. What now? Draw some, you want some variables anywhere? Anything else? What's that? Yeah, wouldn't it be nice if we knew what the area of a cylinder was? So this is a good time to bring up a point. The difference between knowing something and understanding something. All right? I went to a new page because I want to talk about this. If you ask me right now what the area of a can is, I would tell you, I don't know. It's sitting on a page. It's on a formula sheet somewhere, right? I don't have it memorized. But, so I don't know it, okay? I don't know that formula. But I understand where it comes from. So I'm going to come up with a formula without even looking at it. Here's a can, right? It has a bottom and it has a top, right? Both of those are circles. What's the area of a circle? So if this is a radius, right? Then the area of that top one is pi r squared. And the area of the bottom one is pi r squared. And so I have two of those, right? 2 pi r squared. That takes care of the top and bottom of the can. Now I just need the outside of the can. So what I'm going to do now is I'm going to come in here and I'm going to take the can. Imagine that I've taken the tops off. I'm going to cut the can up the side and I'm going to roll it and lay it out flat. What is it going to be? What shape is that? Rectangle. Okay? That's my can laid out flat. The height of the can, which I can call H, would be this side. And so all I need to know the area is how long this is, right? How long is it? If you look at this and you come in from the side like this and look at that circle, isn't this distance around the outside of the circle the same as that edge, right? And that's the circumference of the circle. So I do need to know what the circumference of a circle is. The circumference of a circle is 2 pi r. So the area of this piece is 2 pi r h. It's 2 pi r times h. That's my area. So I just add that to this up here. And that is the equation for the area of a right cylinder. You could check it. It's right. Right? So that's the difference between knowing something and understanding it. A lot of times if you understand something, you never need to memorize it because it's always there. Now, it took me a little time to get it, right? But, okay, back to this. So the area is 2 pi r squared plus, what was it? 2 pi RH or HR, doesn't matter how you do that. That is my area. Now, I better label my cylinder. I better draw some variables on this. I called this the what? H. And then the distance from the center out to the edge here was my R, right? Any questions? So I told you I was doing those faculty observations, right? It doesn't seem right. When I'm sitting there watching someone teach, it seems like it takes forever. You know, but when I'm up here, like I can't believe it's already 1:45. Like I need to there's a lot more I need to do today. I'm like, it's weird, totally different perspectives. All right. What now? Constraint, right? So right now we're trying to get our objective equation down in terms of a single variable. How many variables do we have right now? To know the area, I must know the radius and the height, right? That's two variables. Not x and y, but this time r and h. I need one variable. So that means I need a constraint. What's the constraint? The volume has to be 1,000 cubic centimeters, a liter. If you wanted to, well, no, that would be dangerous. No, you have to convert the liters to the cubic unit, cubic centimeters, because your radius and your height are going to be measured in centimeters. So you need a cubic unit in order to do the problem, if that makes sense. That's my constraint. So I can replace in here, right? I can replace V with 1,000, right? But I don't have a V. So what's the formula for volume of a right cylinder? Pi r squared, which is the area of the top, times h, which is like the depth of that thing. So it's almost like a circle, but how deep is the circle? It's h. So the volume of a right cylinder is pi r squared. Why was I going to put over h? Times h equals 1,000. And I'm just going to get rid of the cubic centimeters. Let's just remember everything's in cubic centimeters. All right. Now, what? We can substitute what? What do you want to substitute? I can solve this. I solve this equation for or your choice, right? Your choice. Would what make a difference? Well, I would need to, well then if I would need to solve for r, which would mean I'd need a square root, wouldn't I? Do you understand what I'm saying? Like I could solve this for r. In fact, I think I'll do them both. I'm going to solve for r and for h, just so you can see. All right. How about I do for r first? Let me try and solve for r. Solve for r. That's the harder of the two, I think. First thing I do is I divide both sides by what? Pi h. Then square root. Whenever you take the square root of something, you must do plus or minus. However, in terms of this problem, if r is the radius of a can, you're not going to have a negative radius, right? So I'm going to throw out the negative, but I'm always remembering I always have plus or minus when I do this. So that's my radius. Okay, that's what would happen if I had chosen to solve for r. Now, let me solve for h. And then we'll decide which one we want to use. So if I solve that constraint equation for h, all I have to do is divide both sides by pi r squared, right? So h is equal to 1,000 over pi r squared. So which one do you want to use? H? Yeah, I think H. And the reason why I like H is because all I have to do if I replace H is just replace that last one, right? If I am going to replace R, I'm going to have to replace R here with, well, R squared. Couldn't I just use this for R squared? Yeah, sure. And then for here, I'd have to use the square root. Ooh. And then I'll have to take a derivative. Ooh. right? The h is under a root. No, thank you. Could we do it? Yes. Do we have to? No. Let's do this instead. Okay, so now we go back to our objective function. Our objective equation came from up here, is now area equals 2 pi r squared plus 2 pi r, but h is 1,000 over pi r squared. Yes, which we're going to clean up. Is that okay? So I am going to notice that I'm going to get a pi to cancel here. In fact, another one's going to cancel. One of my r factors is going to cancel, right? I can multiply 2 times 1,000 to get 2,000. Yeah. So watch what I do now. Instead of just a, I'm going to write a what? A of r. And 2 pi r squared plus 2,000 over what? R, just r. This is our objective function in terms of one variable. So I was calling this up here my objective equation because it wasn't a function of a single variable yet. I'm calling this my objective function because now it is a function of one variable. What should I look at next? Domain, thank you, yes. You need domain. Why is domain so important? That's going to be closed interval or open interval method. That's what it determines. So tell me some restrictions on R, because that's your variable. Can't be 0 or negative, right? Why can't it be 0? The fence could be 0. We said it didn't make any sense, but the fence could be 0. Why can't R be 0 here? In here, right? Yes? But also think about this. The can must hold what? 1,000, 1 liter. How can you have a volume if you don't have a radius? If your radius is 0, your volume is 0. See, with the fence, we were allowed to lay 50-50 and still use the 100 feet of fence. It still made sense even though our pen sucked. It wasn't a pen, right? Here, we cannot say R is 0 because then volume would not be maintained. So R cannot be 0. Is there a largest radius that I can have? Is there a largest radius I can have? Well, according to my program, yes, but imagine this can, right? This can that the edge of it's here, right? The other edge is in Austin. Right? Very infinitesimally thin can. Can it hold 1 liter? I mean, theoretically, could I have a can so thin? Theoretically, yes, right? I know, like, physically we run out of space in terms of, like, size of atoms and things like that, but theoretically, there is no limit to how thin the can be and how wide it can be. So our radius can be as big as we want, which means that we cannot constrain it to a closed interval. Our radius is between 0 and infinity. In other words, 0 to infinity. We are on an open interval. Hey, what if you have an interval where you could have 0, but this was infinity? What type of interval would that be if you had, like, bracket on the 0 and infinity on the other end? It would still be open. It's called half closed or half open. To use closed interval method, you have to have closed, closed. Both sides have to be brackets. Any other variation of an interval, you have to use the open interval method. All right, open interval method time. So what do I need for open interval? Derivative. So my derivative, a prime r, is I'm taking the derivative of this with respect to r. What's the derivative of 2 pi r squared? 4 pi r. This is the same as 2,000 times r to the negative 1. So we did that earlier, so negative 1 comes out. So this becomes what? The derivative? Minus 2,000 over r squared. Yay. We're going to have to set that equal to 0, aren't we? Which means we'll have to have a common denominator. I'm going to do that in a minute. I'm going to set it to 0 in a minute. Let me go ahead and get the common denominator now. You multiply the top and bottom of 4 pi r, top and bottom by r squared. So you get 4 pi r cubed minus 2,000 over r squared. Here's my derivative. Now, when is this derivative 0? When the numerator is 0. So let's go ahead and solve for r. Move 2,000 over, divide by 4 pi. So what would happen if I divide by 4 pi? 2,000 divided by 4, 500. So what is it? 500 over, what's still down there? Pi. 500 over pi. Questions? Dividing both, move that over, divide by 4 pi, you get this? Are we done? Nope. Cube root. The cube root of 500 over pi is my critical number. That's the exact answer. I can get a decimal for that in a minute if I need it. That's the exact answer. Whatever 500 divided by pi is, take the cube root of that. That's a critical number. Any other critical numbers? Anywhere where the derivative does not exist? 0, but 0 is not in the original domain, so I don't need to consider it, right? 0 will screw this up, but 0 is not here, so who cares? So those are my only critical numbers, or that's my only critical number. So now what do I need to do? What's that? Number line. Where on this number line is the cube root of 500 over pi? So I have no idea where that is. Okay, I know the 0 is over there. It's 5.41. So you might need your calculator to actually do 500 over pi cube root to get an idea of what to pick over here, right? Because it's got to be to the left. You can't just be like, yeah, I think 1 will work. Like, you have to know that 1 will work, right? And then you have to pick something bigger than this, which 10. So let's say I didn't want to use my calculator on this part. 500 divided by pi. What's pi? About 3 something. 500 divided by 3. 500 divided. What's 600 divided by 3? 200. What's the cube root of 200? Smaller than 200? I mean, I'm just saying, what if I pick, 100,000? Can I feel pretty safe that that's bigger than this? Yes. I don't need a calculator for that. Okay, so now I'm going to plug these values into my derivative. No. A prime 1. So I forgot what A prime was. It was like 4 pi, was it? 4 pi. I'm going to do the one before we simplified. It was, whoa, where'd that page go? Okay, hold on. I got a page somehow this thing got shoved in there somehow. Put it right there. So I'm using this one right here. 4 pi r minus this. Look, I can just look at this and tell what the answer is. If I'm plugging 1 in here, right, that's 4 pi. You plug 1 in here, you get 2,000. 4 pi minus 2,000. It's negative, right? 4 pi is like no bigger than 20. So that's definitely negative. So that tells me that over here, what's happening? What the hell? Over here, what's decreasing? The original, A, right? My area function is decreasing here. Is this good news? I'm looking for a minimum, right? So it better go down than come back up. So that's good, that's encouraging. And then plug in 100,000. Well, again, what's 100,000 squared? Huge. 2,000 divided by that is smaller than 1, right? Yes? And so 4 pi times 100,000, that's huge. So a huge positive number minus a number that's smaller than 1, that's going to be positive. Now, you could go plug them in and convince yourself, but I'm just doing it by inspection. Now, this number is in our domain, right? So it's a valid number. That means we have a minimum here. That's the only minimum we have, too. So we have A has a minimum at what? At R equals the cube root of 500 over pi. Now look, I want to point something out. On your exam, which is going to be next Thursday, right? We moved it back one class period. If you do all this work, okay, you set this all up and it's all great and you get all this and you come here and you get that and you box it and you move on to the next question, you are not done with this problem and you're going to lose points. You must show me it is a minimum, which means you must construct this. You must verify it is a minimum. A critical number does not guarantee a minimum. Just because you find that number doesn't guarantee it, right? You have to show the down then up for this to work. That would depend on what you're being asked. In this problem, what are they asking for? Because I'm not done with it. I'm not done either. I'm still not done. They're asking for what? The dimensions of the can. Now, if they wanted to know the surface area of the can, you know, find the minimum surface area, then you would actually have to plug this into the original function, wouldn't you? Well, into our A function. But that's not what they want. They want the dimensions. So far, what can I tell you? The dimensions of this can, the radius must be this. What do I still need to determine then? The height, right? It's a can. I need to know how wide it is, how tall it is. How am I going to figure out what the height is? I go back through my work and search for, right, a height equation, because I know I had one somewhere in here, right? That connects my height and radius together. So now I need to write that down and replace R with, yes, all that. Can you tell I like this stuff? H is equal to, I really do enjoy this stuff. I mean, this is like, you know, real life applicable sort of math. Pi over R squared. So pi over R, which is the cube root of 500 over pi, goodness, squared. Do you agree that that's your height? Okay, so for the sake of moving on to another example, somebody tell me what that is on their calculator. I know we've already got work in here. What do you get? 10.839? Approximately. Okay, let's say, and what did we get for radius approximately? 5.41, what? 9? Okay, that's correct. Does anybody want to make a guess, venture a guess as to how this works for all cans, no matter what the volume is? Look at the radius and the height. It's doubled or halved. It turns out that if you're going to build a can, doesn't matter what volume you want, 1 liter, 1 gallon, if you're going to build an aluminum can, the optimum dimensions to use the least amount of aluminum is that your radius needs to be half the height. Or what the radius is half the diameter, right? So if you double the radius, that's your diameter. Your diameter has to be equal to your height. The width of the can has to be the height of the can. That's the optimum dimension. What's up with Monster? They don't care. Just throw money away. They don't care. Because they charge like $5 for that. I'm kidding. So why is that can not, why are they not using that? No. Look at the can. Look at the can. Is that a right cylinder? Okay. Can I see your can? Do you mind if yeah, finish it up. After I touch it, you may not want it back. Thank you. Okay. So your standard can, right, is not a right cylinder. Has that thing. What's that? It's a pressure release, right? When these things get over pressurized, this on the bottom pops out so that the can doesn't blow up. Okay? So that is a little cone, a little dome that will pop out the other way to relieve the pressure inside. So you got that. Monster 2. Finish it up. I'm going to need that can. Finish it up. Okay, not only that, but you got this upper lip that's the way that they seal the top part on, right? You know what I'm saying? This is a separate piece. This is all one piece. It's all one piece, but the cap is different because they run this through the machine, they fill it up, and then they put the cap on later. So that's a separate piece, and I believe that they make it this shape so that they can stack them, right? Make sense? Then you have the tab, right? And this whole shape in here is different. So it's not a perfect right cylinder, is it? So what you would need if you were Monster Company is you would need a function that represents the surface area of this. Then you could optimize it, which I'm sure they did. All right? Or if it's like minimal differences in cost, they may not care. I mean, because they may say, you know what? The fact that our Monster cans are tall makes them badass, and so we would rather have them be tall and badass than to save the little money, because we'll make more money on just the fact that they're badass. Does that make sense? I mean, it's true. I mean, there's so much that goes into the advertising and this labeling and stuff like that. But from a purely mathematical business model thing, if you want to talk about aluminum, this is the type of thing you'd have to do. So if you go back and you look at like 1940s, 1930s, military supplies, you know, you go buy motor. Has anyone seen like a 1940s motor oil can? No, the ones that you open with like an old, like a thing that goes, like you have to hold the little thing. Have you ever seen those? Okay, go Google it. All those cans, diameter is height, diameter is height, diameter is height. That's why they look like that. They look all weird. Why does a can look like that? Well, because that was the optimum way. You done? Okay. Thank you. Glad you brought that today. It was. We talked about the recycling already, right? We don't care, right? Sun's going to expand. Everything's going to get recycled. No worries. No worries. So I'm just temporarily holding it there, which will be temporarily held somewhere else until the sun just converts it all over to its original form. Can you appreciate, at least in that problem, the fact that it's not as simple as 25, 25? Yes? All right. Thursday. Mm-hmm. We're moving that test back. Find the point. On Tuesday, we're going to walk in and you're going to have an in-class quiz. It'll be a just you quiz, not group quiz. It'll be one optimization problem. It'll be one that you haven't seen, okay? It's required I give this quiz. The entire math department gives this quiz. It's the same problem. The what? It's optimization. That's all I can give you. I can't give you an advantage over anyone else only because the whole idea is to just do like just a cross-section test of what students are actually learning. So it makes no sense. I mean, I could sit here and I could do the problem, and that way y'all, I turn in the test, and yeah, they all kicked ass, That defeats the purpose. But we're all doing it at the same day. Oh, no, it's the same type of problem. It's not the same exact problem. Yeah. We know how you all work. So it'll just be a thing you do in the beginning of class. All right. Let's look at this one. We have about 30 minutes left. I think probably about 20 minutes. What review? I haven't made it yet. I have to look into it. Another reason I'm pushing it back is because I don't have a review yet. I'll get one for you. Don't worry. All right, let's get through this. Find the point on the graph y squared equals 4x minus 1, which is closest to the point 3, 1. This is now completely different than anything we've done up to this point. What does y squared equals 4x minus 1 look like? It's sideways parabola, you can tell right there, right? Okay, but you kind of need to know that from conic sections in college algebra or pre-cal, conic sections. Y squared, if it's x squared, it goes up, right? Y squared, it goes sideways. So this is a sideways parabola, and we're trying to figure out where on that parabola we are closest to the point 3, 1. So here's a picture. Here's the point 3, 1, right? Here's our parabola. Here is a point on the parabola. The distance right now between these 2 points is 4.748. As I move along the parabola, that distance just got smaller, right? 3.596. 3.3. Where is it going to be closest? 2.3. Right in there somewhere, right? I think I just went past it. Right in there? Somewhere in there. Yes? Where? Exactly. Exactly where? So, yeah. So here we go. Snap to solution. There it is. Oh man, I forgot to do this for y'all. I'm sorry. Look on this one, the can one. I forgot to graph the surface area function. Remember how we had the area function? Remember that? We had the area function? I never graphed it for you. That's the graph of it. And we found the lowest point. What was it? R was 4.5. So the lowest point is at 5 point something. You can see right there. You see? We translated the whole word problem into a function, and we found the lowest point at was 5 point something. Okay, so for this problem, first of all, let's talk about why we would even want to look at something like this. Because let's say this is a planet, and let's say this is the orbit of something big. right? It's coming around to possibly take you out, right? And so you can model what's happening, and you can predict later where that closest point is going to be, right? Like how close are you going to, is it going to get? I mean, you hear about this on the news, like this thing was so close to the Earth, and they tell you it was like 100,000 light years away or something. Or, you know what I'm saying? They say it's like close, but it's like close in astronomical terms. So you could actually determine this thing. Also, I mean, there's a lot of things you could do where you're trying to figure out how close something gets to a point, right? Maybe you want it to be close, maybe you don't want it to be close, depending on the situation. So where's it going to happen? You ready? Let's do it. I didn't even let you answer. You ready? Right? Yes, you are. What was it? Y squared equals what? 4x minus 1. What's the point? 3, 1. Objective. Shall we read the problem again? Find the point on the graph which is closest to this point. Objective. Objective means you're trying to find a max or a min, right? Or optimization is max or min. You're trying to find the max or min here. Min? Min of what? Distance, right? Trying to find a minimum distance. Do you all agree? Distance between what? The point and your graph or your parabola. Yes? So you need to come up with an objective equation that tells me the distance between the graph and the point. Yeah? So here's my objective. I'll call it D for distance. And I have this parabola-looking thing, and if I really didn't know what it looked like, I could just draw a little parabola-looking thing. I could guesstimate that my point's here at 3, 1. And I could just draw some random point on this. It has an x and a y coordinate, doesn't it? And I'm trying to find the distance between those. Notice I didn't try and draw it in the correct position. I'm just drawing it like arbitrarily. Just to kind of get relationships going here. And then D would be that line right there, wouldn't it? Anyone have any ideas? Pythagorean? We could get it from Pythagorean. I think, well, let's just take a poll. How many of you would want to do a right triangle here and try and come up with like how tall and how wide versus how many of you remember the distance formula for finding the distance between 2 points? Or remember hearing of that? This one. The good old distance formula. I don't know why I'm going to write it up here. I should just write it up there, but if somebody gives you 2 points, x1, y1, x2, y2, this starting to look familiar yet? The distance between them is equal to the square root x1 minus x2 squared plus y1 minus y2 squared. That look familiar at all? You could flip those over. It comes from the Pythagorean. It comes from the right triangle. That's where that comes from. So that's like understanding versus knowing. Yes. Oh, okay. I'm with you. Don't get me wrong. I completely support your looking at it as a triangle, because that's a good thing. Either way, it's all good. So is that all right? We have to kind of know that formula, or we have to know to create a triangle from this. So in terms of our point, what is the distance? D is what? Square root of? Go ahead. Don't be shy. You can go 3 minus x, and then you could do 1 minus y. Couldn't you? Could I do x minus 3 and y minus 1? You could do it the other way around also. I'm going to do it the other way only because I want to keep my x and y in front. I'm going to do x minus 3, y minus 1. Don't understand? Hey, that's pretty good. We have an objective equation. Problem with it is that it has 2 variables in it. What's the constraint? Excellent. Right now, when I drew xy, right? When I drew xy, that could be an arbitrary point, right? It could be anywhere. I need it to be on this parabola. The parabola is the constraint, right? The parabola is the constraint. So in this right here, if this is my constraint, I actually have a relationship between x and y right here, don't I? And I can solve this for x, or I can solve this for y. Which would you prefer? It almost is. I'd have to do what? Square root? If I do that, though, I'm going to have to replace this with the square root, and then have to take a derivative later. I'm not quite sure I'm pumped up about that. If I do solve for x, I'll have a y squared in here, and then I'll have to square it. So either way, you're going to have a little bit of algebra to do. So I'm going to avoid the square root. I'm going to solve this for x. Is that all right? Okay, so y squared plus 1 equals 4x. Then what? Divide by 4. I don't want to do that because, I don't know, I don't want to. I'm going to divide by 4. I'm going to multiply both sides by 1/4. Same thing, right? Is it the same? Okay, let's get our constraint. I'm sorry, our objective now. Let's rewrite our objective. D equals square root of, parentheses, x. What's x? 1/4 y squared plus 1/4. Then what? Minus 3 squared. Plus this one, y minus 1 squared. I don't have to change, do I? Y'all still there or not? I think here's what I'll do next. What's 1/4 minus 3? It's 1/4 minus 12/4. So negative 11/4. Any questions? Is my D in terms of a single variable? Yes. So I can look at it as a function of y. Now, right now, I'm going through this mental dilemma because there's 2 ways to go about this. One of them makes it a lot easier, but is difficult to convince students of. The other one is more straightforward, but the derivative's going to suck because we'll have to take derivative of this. So I'm going to show you the shortcut, but and hope that you will buy into it. All right. I've always had trouble with this one part of this in explaining it. Let's say that you have a function that has a lowest point, okay? Function that has a lowest point. Wherever that lowest point happens, I'm going to get a new page here. So let's say I draw a function and it has a lowest point and it happens right here, and we'll call this point C, all right? This is the function f. Do you believe that if I then ask you to square f, which would be a totally different function, wouldn't it? F squared versus f. If I ask you to square f, it would look like something else, wouldn't it? Now in this case, it might be above it or below it. It depends on how high those points are. But do you believe that if I square f, that the lowest point on f squared is still going to happen at C? The answer is yes. Convincing you of that is not simple to do. You either believe it or you don't believe it. The book just wants you to just believe it. And it's true, and I'm not here to say it's not, but I think that's somewhat difficult for a student to just put their head around. That if you have a function, doesn't matter what it is, and you go and you square it, the lowest points on both graphs don't change. Yeah? No? So do y'all want to go on that and just take that on faith? Is that all right? Or do you want to just, yes? Okay. So if you believe that, then here's what I'm going to do. I do not like the fact that the derivative of this is going to suck, right? It's the square root of something, right? Derivative of square root of something is 1 over the 2 times the square root of all that crap in there. And then chain rule times derivative of everything inside, which is even more, right? So what I do right now is this. I let capital D be equal to little d squared. And if I do that, then this function becomes what? Take the square root away. And that I'm a little bit happier taking the derivative of. Whichever y value makes capital D small will make little d small. Well, whatever value of y makes capital D the smallest will also make little d the smallest, if you believe that, which you said you believe. Okay, so now we have capital D of y is this. Changing it to a function of y. Just notation here. What should I look at next? Domain. What's the variable? Y. Okay, let's go look at our picture. Y is the y coordinate of this point, yes? Is there any restriction, if I'm living on this parabola, is there any restriction on the y value? It can go, keep going this way. It can go forever, couldn't it? It could also go down and the y value could become negative forever, wouldn't it? Yeah? There is no restriction on y, which means that my domain is everything, which means I have to use the open interval method. So now I need my derivative. Capital D prime of y equals, I need to go back to my capital D. How do you take the derivative of this? Because there's a plus here. How do you do a derivative of all this right here? Chain rule. 2 comes down first, then all of this to the first power, right? Times then the derivative of what's inside. I'm going to need this to refer to. So I'm going to move it over here. I'll delete this in a second. So 2 came down. So my derivative of capital D is 2, 1/4 y squared minus 11/4. Then times what? 1/2 y. That's it. That's the derivative of what's inside. Then plus, because I had a sum here. What is the derivative of y plus 1 squared? So 2 comes down, times y plus 1 to the first power, times the derivative of what's inside. What's the derivative of y minus 1? Just 1, so I don't need anything. That's it. That's my derivative. I clean it up. Distribute, oh no, this 2 and this half cancel, don't they? Because that's multiplication out here and out here. So I'm really just going to distribute a y through here, y through here. So 1/4 y cubed minus 11/4 y plus 2y minus 2. Do you agree? Clean that up. 1/4 y cubed minus, what do we have here? Negative 3/4. Oops, negative 3/4 y minus 2. Crud. I don't remember how I did this. Let me check to see real quick if I took this out of the book or not. Does anyone see the problem I'm about to run into? Anyone see the problem? What do I have to do with that? Set it to 0. And how do you solve that equation? What's that? Yeah. There's a problem solving that. It's not a quadratic equation, right? It's not quadratic. It's cubic. But there's 3 terms. There's not an easy way to do this. But we're going to keep moving on. Let's see what happens. Let's take the derivative. Let's set it equal to 0. So I'm setting 1/4 y cubed minus 3/4 y minus 2 equal to 0. I don't like the fractions. I'm going to multiply everything by what to get rid of the fractions? 4. So y cubed minus 3y minus 8 equals 0. Y'all with me? Yeah? What is that thing? Why is that there? So what was it? Or you know what? Let me try and do this. Let me try and factor it. Factor, what was it? Y cubed? No, 4y cubed? No. Y cubed minus 3y plus 8? Minus 8. Damn it. I was hoping that that wouldn't happen. Well, on a test, I would not give you something that couldn't be solved. But I mean, it goes to show you that, you know, there is some issues we have here, right? Now, I'm a math person, right? This is a good lesson. Can I solve that? Not easily. Not easily. We are limited. I mean, we know how to do, there are certain things that we could try. We could try the remember that thing called the rational zero test, where you do all those little synthetic divisions and try and make it factor? That would work if it was factorable, but it's not factorable. But there are solutions. So how would a computer do it? Remember I showed you the intermediate value theorem and the mean value theorem, where it would cut the interval and then cut it in half and cut it in half and keep looking for a change in signs? The computer can do that. So I'm going to use the computer to do that. On a test, quiz, whatever it would be, this would be solvable. It would be quadratic, okay? So you could solve that. So let me go back to this, and let me just come up here and I'll just put solve. I guess I should put equals 0. Oh, shit. No, well, that's a problem. That's a major problem. There's something off then. Are you sure we wrote that down right? No, I mean, we did all this right? Minus 8, derivative, hold on. For x minus 1, we solved for x, we plus 1 divided by 4. That's all good, right? Came in here, we replaced our y, no, our x with that. Minus 3, we had y minus 1, was that right? X minus 3, y minus 1. That's all good. I'm just checking everything to make sure I didn't make a mistake. I won't include you on this. This is 12 over 4, 1 over 4, take away that. Okay, we squared, that went away. It was plus here. I don't see any issues. No. Oh, don't worry, this will not rest well with me. Okay, let's just double check the derivative. The 2 came out, that's the inside. Then the derivative of the inside was this, plus the derivative of the other one, distributed 2y minus 2. Do y'all see anything? I don't see anything. Was our function the correct function? These 2's canceled. Y cubed, y. This is 8/4, negative 3/4, 0, 4, 3. Where? It would have gone here and here, but then we would have come through with a half anyway, and it would have undone everything. Okay. Let me go back to this. Solve this for x. Frickin' Robert. It's Fiesta. It's time for Fiesta, all right? Okay, look. What's wrong with this? Why is this? Solve for x. Frickin' idiot. Doubt the math. Okay. Now, it's smart enough to grab the imaginary solutions too, but remember in college algebra, if it's a third-degree polynomial, there's 3 solutions, and imaginary solutions come in pairs, so we'll have 3 total solutions. One of them is real, the other 2 are imaginary. We don't need that. All we need is this, 2.492. All right? So, after fumbling that up a little bit, y is 2.492. That 2.492? Yes. This you couldn't do by hand easily. Now, in the next section, which is called Newton's method, we actually have a way of doing that. In fact, I think I will use this example to do that, because that's a great way to show you that there is a way to get this, but you don't know how to do it yet. So let's just trust that that's the critical number. Are we good? I want to finish this up. I'm out of time. Yes? Oh, yes. That's what they're doing. Yeah. 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 Yeah, but if you ask a computer to solve for X when the equation's in Y, it's going to go and look at you and go, shut up, which is what that one just did. Okay, so I'm sorry. I have to finish this. Number line out. Do we have any other critical numbers? No, because it's never undefined. I'd go here, 2.492. I'd break it up. I'd pick two test numbers. I would figure out that capital D went down, then capital D went up. So we would have a minimum at Y equals 2.492. I'm not going through that, but you could do that, right? Testing. You're plugging these numbers, these test points, into what? The derivative, right? I'd plug in like maybe 1 and 3. Now, I need to know what X is also, right? Because it says find the point that's closest. I have the Y coordinate. How do I get the X coordinate? I go back and I find my equation that had X in it. There it is. And I replace my Y with 2.492 or 494 or whatever it was. Plug it in here, and that gives me my X. Is that all right? Does that match what I had here? Snap to the solution. Close. I had the computer round it. 2.5 was the Y coordinate. If you do the X, you'll get 1.8. All right. Here's the graph of that function. Now, I'm pretty sure when I did this on the computer, this is not capital D. This is probably little d. Okay, that's so. Sorry about that. You probably want something to practice, right? Of course you do. Number 9. You have to guess. Let's just say, yeah, do all number 9s. Page 238, number 9. Number 11. $15. This one, number 25, is a problem I've given on tests before. We're pretty much done, but I also think you should also look at example 1 in the section. I think if you look at those, you'll be at least in some decent shape for the quiz that we'll have on Tuesday. All right. Have a great fiesta weekend. You want to go do it? Go do it. Yep. Just real quick. Yeah.